So here's what we've got. So we've got projectives in O. And this is equivalent to this thing called S. Then there's the graded version of S. This is not an equivalence, but there's an obvious functor where you just forget the grading. You can take a graded module and regard it as not graded. And then this is equivalent to parity sheaves. And then you have to pay attention to there's a little bit of subtlety in what goes on here. So you have to prove something about what indecomposable modules do when you forget the grading. But I think probably I don't really have time to discuss the details. But let me tell you the theorem that comes out. The theorem that comes out of this is that so I began the lecture by reminding you of the main problem from Monday and the main problem from Tuesday. And the theorem is that these problems are equivalent. So the theorem is that if you want to know the multiplicity in nabla y of the simple labeled by W, this is equal to the total rank. So I want to take all the cohomology sheaves of curly EW and restrict them to this Schubert cell. So you have to pay a little bit of attention. I swapped where y and w are compared to the beginning of the lecture, but I have to make that swap to make this equation be true. And so the proof idea is somehow the hardest parts of the idea I've already shown you. It's that this category of modules over the covariant algebra connects this side to this side. So I talked about what projectives do and what parity sheaves do. You have to pay a little bit of attention. You have to pay more attention to what V does. I mean, you can plug in something that's not projective, like you can plug in a nabla into V, and you can plug in something that's not a parity sheaf, like you can plug in a constant sheaf on XY circle extended by 0 into H. So you have to pay attention to you have to study these in a little bit of detail. But anyway, I think the hardest part of this theorem is, or maybe the deepest insight that's needed to get at this theorem is setting up this picture. And once you've set it up, then getting from here to here is relatively straightforward.
So we still have a theorem that parity sheaves are included exact triangles with extensions by 0.
Yeah, that's right. So you can do something like resolve one of these things by parity sheaves, and you can resolve one of these by projectives. So that's one way to get at this kind of equation. Okay.
But the proof just seems kind of indirect, right? You're just sort of computing the two things almost, and they're the same.
The proof is a bit indirect. Yeah. There's not a functor. It's not of the form. There's not like a formula that you plug a parity sheaf into where you get out an object of category O. So in that sense, it is indirect. I agree.
But if you know some kind of a physiology statement, you can get to that or not.
Causal duality statements tend to involve some version of this anyway. So I think causal duality can give you statements that you might enjoy more or less, depending on how you how exact you like your things to be. But I think it doesn't escape this kind of going through modules over the covariant algebra. Okay, so somehow the motivation for my whole series of lectures was to tell you something about the Lustig conjecture. So I didn't actually tell you on Monday what the Lustig conjecture says. So what it is it's a formula for these multiplicities for some very special highest weights, but in the category of representations. And you can take that formula and see what it implies about category O. So Lustig's conjecture for the principal block of rep G implies a formula in category O. And here's what it implies. Let me get the statement correct. So the statement is that the multiplicity of LW in nabla Y should be equal to the Kazdan-Lustig polynomial PYW evaluated at 1. And so let me remind you that these Kazdan-Lustig polynomials had a topological interpretation. PYW of Q was it was some kind of rank formula like this, but for ICs. So it was minus LW plus 2I of ICWC restricted to XY circle times Q to the I. And so a corollary of this theorem, so this is a theorem of Zergel. The consequence of Lustig's conjecture for category O is true if and only if, for all W in the Weil group, EW of K has the same stock ranks as the IC. So it has the same table of stocks. As ICWC. All right. So now we're getting close to the end. So the very end of Tuesday's talk was about Williamson's recipe. So from lecture 2, so I'll remind you sort of what the input and output of this were. So the input was you choose a bunch of permutations. I'll call them sigma 1 through sigma m in some symmetric group called SK. And then you choose some integers, the same number of integers, am, so these are non-negative integers. And then I had an assumption that the sum of the lengths of these permutations is equal to the sum of the AIs, and let me get the condition right. I wanted this to be equal to n minus k. So k is the same number as in this symmetric group, and n is some larger number. And then I defined a new integer. I called this C on Tuesday, and today C has been the covariant algebra, but maybe that's okay because one of the C's is an algebra and the other C is an integer. So anyway, the formula for C was a calculation in a polynomial ring where you do a bunch of multiplying by variables. Let's see. And then applying these divided difference operators, and divided difference operators, in some sense they behave like a little bit like partial derivatives, and they reduce the degree. So one thing I said on Tuesday is that this assumption that the lengths of the sigma i's add up to the same number as the ai's, it means exactly that the increase in degree you get from these monomials is exactly canceled by the decrease in degrees you get from the divided difference operators. And so this is an integer. And then, so Williamson's recipe gave rise to two elements, y and w, in the symmetric group on capital N letters, such that the ranks of the parity sheaf on those two strata disagreed with the rank of the IC sheaf on those two strata, as long as if C is not invertible in K, which is equivalent to saying if C is 0 in K. So now this sets you up to try to find a situation that contradicts the Lustig conjecture.
Is TK a root?
No, TK is a variable in a polynomial ring. So
I guess, like, is it an xi minus xj or is it xi?
It's xi.
Okay.
Yeah. Yeah. So you can just do this by hand. You can pick your favorite small integer k and pick a handful of permutations, and you can compute an integer like this. So here's So let's try to contradict the Lustig conjecture. So the first attempt is pick some sigmas and a's and just compute. Okay, so this capital C, it's an integer. If C comes out to be plus or minus 1, then you get no contradiction, because that'll remain plus or minus 1 in every field. It's never 0 mod anything. So there's no contradiction. If C is you can prove that C will never be 0. So if C is different from plus or minus 1, and it's automatically going to be different from 0, then, well, do you get a contradiction? You get a contradiction if the characteristic if the characteristic divides that integer. But the characteristic, well, let's go back up here for a second. This corollary is about representation theory. So P has to be bigger than H here. Then you get a contradiction if what? If there exists a prime factor P of C. So if you find a prime factor P of C, then that's going to be a characteristic where C is congruent to 0, and where these ranks will disagree. But in order for that to be relevant, that P prime better be bigger than the Coxeter number, and the Coxeter number is capital N. So if you get a contradiction, if there exists a prime factor P of C such that P is bigger than N. And if you start trying this by hand, I think it's not so hard to come up with a case where capital C is not plus or minus 1. But in the smallest cases, capital N ends up being quite large. And so you don't get a contradiction for Lustig's conjecture. You have to look for a while until you find one where there's a prime factor of C that's larger than capital N. And the first family of these that was found by Williamson, or maybe Williamson and He, went like this. So they explained, this is something that it's written down in a lot of concrete detail. You can really get your hands on this. So they pick the sigmas and a's by a repeating pattern. And the number of times you, and they computed C in general for this pattern, and it turns out that if you repeat the pattern k times, maybe I shouldn't use k because k is something else over there. Repeat the pattern, how about m times, and then they showed that C is the nth Fibonacci number. And the pattern is not very long. It's I think there are two permutations and two integers here. So you just keep repeating the same two over and over. But if you repeat them, then that means that these sums get larger, which means capital N has to get larger as well. And so with this setup, it turns out that capital N, let me tell you what the formula for capital N is. Capital N is 3m plus 2. And so now you can just try this for yourself. Start listing Fibonacci numbers and see when you find a Fibonacci number with a prime factor. See when the mth Fibonacci number contains a prime factor larger than 3m plus 2. So the first counterexample to the Lustig conjecture that you obtained by this method occurs when m equals 11. So I want to emphasize that this is by this method. This recipe has a huge amount of flexibility. So there are lots of different things you can do. So when m equals 11, the 11th Fibonacci number is 89, which is prime. But capital N is only 35. So this tells you that for the group SL35 in characteristic 89, there's just a Weil module whose composition multiplicities are not as predicted by the Lustig conjecture. Okay, so maybe just to wrap up, I'll tell you about an improvement of this result, which is in the same paper. So you can keep going with this method and just like write down bigger and bigger Fibonacci numbers, and you can find lots more counterexamples. But you might ask the question, well, this shows that if you want the Lustig conjecture to be true when p is bigger than h, well, it doesn't work. This right here is a counterexample. But maybe you can just modify the bound a little bit. Maybe maybe the Lustig conjecture is true when the prime is bigger than 2h, or 3h minus 3, or something like that. There's a ton of results in representation theory where there are these like minor variations on like easy formulas in terms of the Coxeter number beyond which things work the way you would like them to. And so the question is there some could there be some easy formula in terms of the Coxeter number that beyond which the Lustig conjecture is true? And the answer to that is still no. So this is part 3. So this is due to Kantarovich, McNamara, and Williamson. So they use a slightly more complicated repeating pattern. So the problem is that Fibonacci numbers themselves, they're something that like a lot of people learn about them in middle school or something. They're elementary, but they're also kind of super difficult. So rather little is known about the growth of prime factors of Fibonacci numbers. But Fibonacci numbers, I mean, I guess Fibonacci numbers came up here because it's like a, it's like a cute thing. but if you could replace those with something where you understand the growth of prime factors, you could do much better. So they use a slightly more complicated repeating pattern of sigmas and a's to produce a sequence of integers c's whose prime factors such that such that the largest prime factor of the nth constant that you're producing this way, of the nth integer c. What I want to say is that the prime factors grow exponentially fast. So I have the largest prime factor of the nth integer in the sequence to be bigger than some constant times times e to the m or something. And this means that that no polynomial in the Coxeter number, no polynomial every polynomial grows more slowly than an exponential. So no polynomial in the Coxeter number can be a bound beyond which the holistic conjecture is true. Yeah, no polynomial in the Coxeter number can be a lower bound for the validity of the holistic conjecture. Okay, so I'll stop there.
Are there any questions?
Is there a formula for the degree in the cohomology where you rates differ or the rates differ?
There's a degree where they're guaranteed to differ, and it's based on the difference in dimensions of the two orbits.
But it's like not.
The thing is that the problem I stated from at the end of as going the Tuesday lecture was to compute the table of stocks for a parity sheaf. And so something that I really want to emphasize is that this whole Williamson's recipe stuff, it doesn't solve that problem. Instead, it circumvents it. We're not able to compute, you can't pick your favorite biogroup element and ask for the table of stocks. That's intractable beyond low ranks. What this does is you feed in some input and you get out a W that you didn't know in advance and a little bit of information about where its table differs from something you might have predicted. You don't get the whole table. You get very little information, but just enough to contradict the Lustig conjecture.
But I guess, the difference is in degree L of W minus L is what, like negative L.
They're guaranteed to differ in that degree. Beyond that, I don't know.
Did people actually take this example and write down SL35 and characteristic 89 and show that the multiplicity actually compute with the modules?
I think actually computing with the modules is really difficult. I mean, somehow I think the linear algebra you have to do is I think intractable.
So you can't even check to make sure just by using it.
Maybe you can, but I suspect that the limitation will be computational power.
Does all this theory give you some uniformity of the Lustig conjecture, which is true in some other setting, like for projective modules, tilting modules?
So tilting modules are kind of a separate story. So somehow, I guess the idea of tilting modules has been around for decades. And I think what's become increasingly clear. I don't know. I don't know what people's opinion on this was in the 80s, but I think now it's kind of clear that tilting modules are just easier than irreducible modules. So there is a character formula for tilting modules, which has which is related to, which is geometric in nature, which is about parity sheaves. So this is, characters of tilting modules, and it definitely involves related ideas to the things that I've been talking about in the mini course. So this is, there's a conjecture of Riesch-Willingsen, which is now proved by myself and Mackie and Riesch and Willingsen. So according to the introduction to the Riesch-Willingsen paper, there's some remark of Anderson which lets you deduce the characters of simple modules from those of tilting modules if the characteristic is bigger than, I don't know, 2h minus 2 or something like that. But I don't exactly, I haven't understood how this works. So and I think my impression is that it's not like a closed formula. It's a method for computing them. But maybe that's all anyone can expect for anything. So yeah.
I'm just wondering, what's the smallest point for a counterexample? Is it 89 in the second one?
I don't know the answer to that actually. I'm pretty sure that this is not the smallest counterexample. But I think you have to ask Jordy that question. So either one of you.
I can't see behind me, so anyway, how much freedom does Williamson's recipe give you to, like, how much control do you have? Like, they produced the Fibonacci numbers here. You can produce things here. Like, I guess
the flavor of this is you're taking like you start with this monomial which involves a single variable, and then you apply something that is roughly like a partial derivative that may introduce other variables. Like it's a directional derivative, maybe I should say. So it can introduce other variables even though you start with only one. And then you multiply, differentiate, and then you get an integer at the end. So anything you can do with that, there's quite a lot of freedom.
okay.
Yeah.
Your PYWs up there, so those are just ordinary Kazan-Lustig.
Those are ordinary Kazan-Lustig polymers.
But Lustig's conjecture in terms of affine.
So ordinary Kazan-Lustig polymers are a special case of affine. So basically, I didn't write down the full statement of the original Lustig conjecture, but extracting this from that is basically a matter of sort of figuring out how some cosets line up inside the affine Biogroup or something like that. So
it's like once you go into that category O, it just turns into a statement.
Exactly, and that was Zergel's original purpose. Somehow like category O is set up in order to simplify the statement of Lustig's conjecture that involves only the Kazan-Lustig polymers for the finite Biogroup. So it was set up to make that happen.
Would proving that consequence basically is knowing those multiplicities enough to work it out for the rest? Or?
No, I don't think so. I think like if Lustig's conjecture for category O is true, it's not an immediate consequence that Lustig's conjecture is true. So
I think that's somehow. You shouldn't believe it because you can still find a bound on P, which will work for category O.
yeah.
There are much more elements.
Exactly. Yeah. This is like a piece of Lustig's conjecture. So the category O part is kind of a piece of it, and it could happen that in some characteristic it's true in that piece, but not true somewhere else that you mod it out by or something.
Okay, if there are no further questions, let's thank Pramod for these wonderful lectures.